Hello again. Today we're going to review Newton's third law of motion. This video will be a little bit of review and also a complete summary of Newton's third law. Newton's third law says that for every force there is an equal force in the opposite direction. You'll notice this might be a little different than you're used to hearing from other sources. Please have this definition in mind. This is the definition I want you to know. Other definitions are usually a little bit vague and maybe even misleading or maybe even false, depending on how they're worded. So this is the definition I want you to know. For every force, there is an equal force in the opposite direction. Now, what does that mean? Let's give it a try. Here is a person pushing a desk. He's pushing the desk to the left. Now, if he's pushing the desk to the left, then there's a force on the desk to the left. Therefore, we can draw a force diagram for this desk. And we can see that there is a force, a push, to the left. It is from some object, and it is on some object. Just like we used to label fully the forces, like this. Now, what are those two objects? It's pretty clear in this example. The force push is from the person, and it's on the desk. Okay, well then, if this force push exists, then Newton's third law says that there's another force that is equal in size and opposite in direction to this original push. But what is that force? This force is really very easy to find if you write these full labels out. The Newton's third law pair is the force created or found just by switching the two objects. It'll be the same kind of force. It'll be a push also. And instead of being from the person on the desk, it'll be from the desk on the person. And if it's on the person, then it goes on the person's force diagram. So let's draw that. It'll be the same size and the opposite direction. So we label that with an arrow and hash marks. It is also a force push from some object on some object. And as I said before, those two objects this time are just switched around. The desk is now the one doing the pushing. The person feels it. And that's how Newton's third law works. You'll notice there are a couple things to notice here. All I did was switch the order of the two objects. A force push from the person on the desk means that there must also be a force push from the desk on the person. And if the two forces are on different objects, the objects are switched, then the two forces must necessarily, they always go on different force diagrams. That is always true for Newton's third law of forces. If one force is on one object from the other object, object 2, then this other force, the paired force, comes from object 1 and it's on object 2. So Newton's third law forces are never on the same force diagram. They're always on different force diagrams. One more thing to notice is that the two forces will be the same type. So for example, if there's gravity force exerted on a person from the Earth, there's also gravity force exerted on the Earth from the person. If there's normal force exerted from object 1 on object 2, then there's normal force exerted from object 2 on object 1, and so on. So let's try one more example. This person is walking to the left. His velocity is this person is walking to the right. His velocity is to the right. He wants to slow down. So his acceleration must be the opposite direction, therefore it's to the left. If his acceleration is to the left, then he needs a force on him to the left. Now what force is that? What force could maybe slow this person down? There are a couple different options, but the most common is probably friction force. Friction force from the floor is acting on the person to slow him down. So therefore, that force goes on the person's force diagram. We can draw it. there is friction force from the floor on the person. And if there's friction force on the floor from the person, then Newton's third law says there must also be friction force from the person on the floor. This is kind of maybe strange, you haven't thought about it, but that means we can actually draw a force diagram for the floor itself. So let's do it. If there's friction force from the floor on the person, there is also friction force in the opposite direction on the floor from the person. From person on floor. And once again, these two forces are exactly the same size, so we can mark that with hash marks. Now, I have not labeled all the forces on the person. There's also gravity force, normal force, maybe air resistance, maybe other things are acting on this person. I have not labeled all the forces on the floor. But what we're trying to do here is just find the Newton's third law pairs. And what we've done is we know that there must be a force slowing this person down, a force pushing the person to the left in order to cause that acceleration. So we guessed that that force was friction force from the floor on the person, acting to the left. Which means that by Newton's third law, there must also be a friction force from the person on the floor. And if you don't believe me that there is a friction force from the person on the floor, then go out and try it. Walk across the floor, and when you slow down, feel which way you have to push the floor in order to get the floor to slow you down. A more extreme example would be running or sprinting. At the end of your run or sprint and you want to slow down, you need to push the floor or the ground forward in order to get the ground to push you backward and slow you down. These examples are all around us. Newton's third law acts whenever there's a force. And as we've seen in the last couple weeks, there are forces all over the place. So get used to doing Newton's third law. It's really very simple if you if you label the entire force from object on another object. And then all you do is switch the objects, keep the type of force the same, and make sure that other force goes on a different force diagram. That's it.